So I've kept up the phase portrait that we drew in the last couple of videos, and I've just rewritten our linear system here. I've done a couple of things. First of all, I gave names, f and g, to the functions that give me x prime and y prime. And second of all, I multiplied things out. Earlier we had these in factored form. That made it very simple to find the null clines. Now, when I'm linearizing the system, I want to be able to take the partial derivatives, and it's easier to have things multiplied out. So remember, when we're linearizing, we're going to switch variables so that u and v we get by just subtracting the x and y coordinates of our equilibrium points, so that we're moving that equilibrium point to the origin. And that's going to be the Jacobian matrix times uv. Okay. And the formula for the Jacobian matrix is the partial of f with respect to x, partial f partial y, partial g partial x, partial g partial y. So let's just get a formula for that. Then we'll be able to plug in the three coordinates for our the three pairs of coordinates for our three equilibrium points, and hopefully classify them. Okay. So f is up here. Partial with respect to x is going to be 6x minus 4y. Partial with respect to y is just minus 4x. Here's g. Partial with respect to x is negative 2xy. Partial with respect to y is negative x squared minus 3y squared plus 5. Okay, so let's take a look at the Jacobian that we get at the equilibrium point 0, 0. Now remember, based on what I see here, I sort of made an educated guess that I think this is going to be a source, although I need to recognize that I did not look at what happened in quadrants 2, 3, and 4. Mathematically, this is defined in the entire xy plane, and it's possible that I do have different behavior from those other ones. So of the educated guesses I made, I'm actually most confident about the guess that this is a saddle because I have information about what happens all around that. Whereas with these two, I don't have any information to the left, or in this case, below it. Okay, so let's see what we get. Plugging in 0 for x and y, I'm going to get 0, and 0, and 0, and 5. So, just using my shortcut to get the characteristic equation, lambda squared. Now here the trace is 5, minus the trace times lambda is minus 5 lambda, and then plus the determinant, which is just 0. So my characteristic equation is lambda squared minus 5 lambda equals 0. So that's lambda times lambda minus 5 equals 0. Lambda 0 or 5, we can't classify this one. Remember, if 0 is an eigenvalue, we can't classify the equilibrium solution. So we're not going to get any more information out of the linear system in this case. The 2 times linearization fails are when 0 is an eigenvalue and when we get a center. Now if I get a center, I do have a little bit more information than if I get 0 as an eigenvalue. If I have a center, I know that I'm sort of spinning around that equilibrium point. I just don't know if I'm getting closer to it, further away, or keeping my distance. All right, so let's see if we have any better luck getting some information at 0, 5. So if I plug in 0, 5, I get 0 minus 20, 0, 0, 0, negative 75 plus 5 is going to be negative 70. Now, neat thing about a matrix like this, it's diagonal. Those diagonal entries are my eigenvalues. If you've had linear algebra, you know that. If you haven't, you don't. So let's work it out. Lambda squared. The trace is negative 90, so minus the trace times lambda is going to be plus 90 lambda. And then the determinant is plus 1400 minus 0. And the characteristic equation, we set that equal to 0. Okay. But I can sort of see how I got that 1400. I can see that this is just going to factor as lambda plus 20 times lambda plus 70 equaling 0, so that lambda is equal to negative 20 or negative 70, which are the diagonal entries. Okay. All right, so those are both negative. So that's telling me that this equilibrium point behaves like a sink. Now that is what we had predicted based on this behavior. Notice that does tell me that if I did extend this to quadrant 2, my solutions over here would also be approaching that equilibrium point. Okay, so now let's take a look at 4-3. That was the one we had predicted was going to be a saddle. So, let's see. That's going to be 24 minus 12 is 12. Negative 16. Negative 24. Let's see. Negative x squared is negative 16. Minus 3y squared is minus 27. And then plus 5. So I think that's going to be a negative 38. Okay, so let's work out our characteristic equation. So I'm going to get lambda squared. Now my trace here is negative 26, so that'll become plus 26 lambda, and then plus the determinant. Now, for the determinant, see, it's that minus that. It's going to be a big negative number. I'm going to actually pull out a calculator. Not that we couldn't do this, but it's just tedious. So, I'm going to have negative 12 times negative 38. So that gives me negative 456. And then minus 16 times 24. That's going to give me, whoops, I got 72 because I made a sign mistake. Okay, so let's see, 12 times 38 is that. Okay. I can do this. Okay, 840. So minus 840. And then, of course, the characteristic equation, that's going to equal 0. Okay. So I'm just going to use the quadratic formula. Lambda is negative 26 plus or minus the square root of 26 squared. Oh, I'm feeling so lazy. 676 minus 4 times a times negative 840. So that's going to become plus 840 times 4, 3360, all over 2. Okay. Now, I don't need to simplify anymore if I can see what the signs of my eigenvalues are. So, that was 26 squared. This is bigger than 26 squared. So, negative 26 minus anything that's not negative is going to give me something negative. But this is bigger than 26, so minus 26 plus this is going to give me something positive. So I do have one negative and one positive eigenvalue, and so this is, in fact, a saddle. Okay. With this example and with the last one, again, I chose to do the phase portrait before I classified the equilibrium solutions. And so this was really just sort of confirming what I saw from the phase portrait. If I had done this ahead of time, might have helped me in drawing the phase portrait. So again, it's a matter of personal preference, what order you do things in if you're doing all of these things. I think we got a pretty decent phase portrait without even doing the linearization, but it's nice to see that the linearization does confirm what we got from that phase portrait.